we've talked about how to find the eigenvectors of a matrix. We talked through this, given the defining equation for an eigenvector, matrix times vector equals constant times vector. That definition led us to this form where we manipulated around. We got to this criterion that for eigenvalue lambda, the determinant of m minus lambda times the identity has to equal 0. We were able to use this to solve for lambda, the eigenvalues, and then we plug those in one at a time up here to solve for the eigenvectors that made it work. That's our plan. That's how we do this. Right now, I want to just do a few examples to show you some of the ways this can come out, because they do differ. Oh, and I'll mention, for a 2 by 2 matrix, it's worth reminding you that this equation winds up being lambda squared minus the trace of m times lambda plus the determinant of m equals 0. That's what this equation always comes down to when you multiply it out. However you find the determinant, you'll get this for 2 by 2. For a 3 by 3 matrix, this is a minus lambda cubed, this is a plus lambda squared, and there's another term. You can't do it for sure. But for 2 by 2, we use this shortcut. It'll help us out for this. I apologize if you hear a grinding noise in the background, by the way. Sorry, just some work being done in the building. But okay, here we are. Here's my thing. So let me do some examples. Let me do some examples of this. First one I wanted to do was this matrix. I want my matrix to be, matrix should be 2, minus 1, minus 6, 3. That's my matrix, and I want to find the eigenvalues and eigenvectors. So here's my plan. I'm going to figure out what that subtracted thing is. That's minus lambda 0, 0, lambda gives me this combination. And so, 2 minus lambda, minus 1, minus 6, 3 minus lambda. That's my matrix, and I want to take that determinant and set it equal to 0. I know what I'm going to get, right? I'm going to get lambda squared. The trace is 5, so minus 5 lambda. The determinant is 6 minus 6 is 0. That's my equation. This is the determinant of this is 0. You can tell it's 0. These are redundant. This is minus 3 times the top row is the bottom row. So it's clearly this is a singular matrix. So this isn't surprising. But this is my idea that this is my characteristic polynomial to find the eigenvalues, and this one's trivial to factor. It's just lambda times lambda minus 5. So my two eigenvalues are 0 and 5. Those are my eigenvalues. I can find my eigenvectors. Well, okay, lambda equals 0 is pretty easy. I do 2 minus 0, minus 1, minus 6, 3 minus 0 times AB equals 0, 0. Always a redundant system of equations. What I get is 2a minus b. Won't cram it in here. I'll put it up on the top of the next one. I get that 2a minus b equals 0, or in other words, b equals 2a. So my eigenvector, my lambda equals 0 eigenvector, is a 2a. Or I'm going to write it as 1, 2 to pick a simple looking example of this. So the vector 1, 2 is an eigenvector with eigenvalue 0, and maybe I won't check that live for you. We could. Yeah, let's check it. 2 minus 1 minus 6, 3 times 1, 2 gives me, that's 2 minus 2 for the top component, and minus 6 plus 6 for the bottom component, which is 0. That verifies that it gives me eigenvalue 0. It's 0 times the original vector. Okay. The other one, my lambda equals 5 case, I'm going to have doing the same thing. I've got 2 minus 5 minus 1 minus 6 and then 3 minus 5 times AB equals 0. And what is it? 2 minus 5 is minus 3, so that's minus 3, minus 1, minus 6, minus 2. AB equals 0, so that gives me minus 3a minus b equals 0, so b equals minus 3a. So my vectors for lambda equals 5 eigenvector, I can write it as a minus 3a, or maybe I'll just choose 1 minus 3. as my eigenvector there. 1 minus 3 is my other eigenvector. And again, let me check that really quick just to see that make sure that it works. I've got 2 minus 1 minus 6, 3 times 1 minus 3. What's that give me? That's 2 plus 3 is 5. And minus 6 minus 9 is minus 15, which is equal to 5 times 1 minus 3. That is indeed an eigenvector with eigenvalue 5. So cool. My process works. This shows the process works. And I wanted to show you this example because it does have an eigenvalue of 0, which is perfectly allowed. If your matrix is already singular, it's got a 0 eigenvalue. So we've got that. Another example. Let me do this one, 2, 3, 0, 2. Here's my matrix, 2, 3, 0, 2. And I want to know, what are the eigenvalues and eigenvectors of this one? Well, what do I have? For this, I'll use my trick again, my shortcut. Lambda squared minus my trace is 4 lambda, plus the determinant is 4 minus 0 is 4, equals 0. I can factor this. This is lambda minus 2 squared equals 0. Lambda minus 2 squared. So my only eigenvalue is lambda equals 2. Just 1. It's the same eigenvalue twice, so it's a multiplicity 2, you might say. But we've got that. I apologize for the grinding noise. It's in construction. It's kind of loud, sorry. But okay, we've got this lambda equals 2. If this later or something, but got this lambda equals 2. I'll use my process again. M minus lambda I times V. What do I get? 2 minus 2 is 0. 3, 0, 0 times AB equals 0. So my only conclusion, that's 0, that's 3B equals 0, and no requirement on A. So that tells me that A0 is a general eigenvector, or I guess I can say 1, 0 works. And you can immediately see, multiplying this times 1, 0 to 0, it gives me eigenvalue of 2. It works. There's not another one. There's no. We only have one eigenvector for this matrix. We have fewer eigenvectors than we have rows and columns. So this is a matrix that just doesn't have a second eigenvector, and that happens sometimes. It'll only happen if you have a repeated eigenvalue. Every eigenvalue must correspond to at least one eigenvector, but it doesn't necessarily correspond to the same number as the number of times it showed up in your polynomial. So there we are. We're short of an eigenvector, just one, and there we have it. So that's an example. Another example. Let me just do one last one, and then we'll see where this takes us. I want to do the matrix. How do I want to do it? Yeah. 0, minus 1, 1, 0. I want to know what the eigenvalues and eigenvectors of this are going to be. And when I do this, well, I can use my polynomial again. It's going to be lambda squared minus the trace is 0, minus 0 lambda, plus my determinant is 0 squared minus negative 1 squared plus 1 equals 0. Lambda squared plus 1 equals 0. That tells me that lambda equals plus or minus I, the imaginary unit. Plus or minus I is my lambda for this. And that's a little weird. I'm not used to seeing, these are real numbers. It's a little surprising to see complex numbers come out. But you can see I've got a quadratic in here. Of course, quadratic formulas, quadratic equations can give you an imaginary part in your quadratic formula. Nothing else for it. Does this even make sense? Well, it can. Sometimes this means there's just no real eigenvectors, so you can't do anything with it. But in this case, we can actually make sense of it. We can do this. What happens? Now, let me choose plus I, just for the sake of doing this. If I do my m minus n minus lambda I thing, I will get minus I 1 minus I times AB equals 0, 0. And so that tells me that minus IA plus B equals 0, or A minus IB equals 0. Same thing. These are, in fact, if I multiply this row by I, I'll get, oh, is this right? Hang on. Oh, minus 1. Good. Right, get this right. Minus IA minus B equals 0. Good. Doing my double check, right? Multiplying this row by I gives me I here and plus 1 here. So it's exactly the opposite. Okay, this is good. That tells me that B equals minus IA. So my eigenvectors for lambda equals plus I, my eigenvectors are in general A minus IA. And maybe the simple case there is to do 1 minus I as an eigenvector. The other thing I could do, I could go through, fortunately the plus and minus works pretty easily here. That was the plus I. If I had chosen minus I, let me put just a minus or plus here. If I put in minus I instead, I'd be the bottom sign of these two. And that would mean that I would have gotten a minus or plus here. So this would have been minus or plus IA. And this would have been, for plus or minus I would have had minus or plus. So there we go. I've got my two eigenvectors. One minus I with eigenvalue plus 1, and 1 plus I with eigenvalue minus I. I get those two, and that's my eigensystem for this thing. I could do a double check just to make sure this works. Let me check the first one. Let me check 0 minus 1, 1, 0 times 1 minus I. If I do this, this gives me 0, so that gives me plus I, and this gives me 1, which is equal to I times 1 minus I, because 1 times I times minus I gives me plus 1. So there we go. We've got this results. We can find, even if they're complex eigenvalues, we can find eigenvectors to go with it that make it work. That's my that's my story for some 2x2 examples of finding eigenvectors. And I think this illustrates most of the things that can come up in 2x2 cases.